There is a room in Nanjing tonight where the air itself is being turned into a highway. No fiber, no copper, no cable buried beneath the street. Just a beam of radiation slicing through open space at 206 gigabits per second, fast enough to deliver every film in the Netflix library before you've finished reading this paragraph. Now check your own phone. On its finest day, standing in its finest spot, it might crawl to 300 megabits. Do the arithmetic. What just happened inside that lab isn't an improvement. It's closer to a different category of physics altogether. But strip away the number, and here's the part that should actually unsettle you. It isn't the speed that has defense ministries and telecom regulators quietly alarmed. It's a chip, smaller than a fingernail, built to do something no chip on this planet has ever managed. What is it? I'll tell you. But not yet, because the chip only makes sense once you understand the trap it just escaped. And that trap has been shaping your life in ways you've never been told about. Consider, for a moment, how much of your existence is held together by signals you cannot see. The phone in your pocket, the navigation guiding your car, the monitor tracking a stranger's pulse in an ICU 3 floors up, the automated arm that packaged the medicine in your cabinet. None of it looks related. All of it depends on the same invisible thread, a wireless signal, doing far more work than you have ever given it credit for. Here is something almost nobody stops to ask. What actually happens when wireless technology takes a genuine leap forward? Not faster video. Something bigger. When the world moved from 3G to 4G, it didn't just speed up your downloads, it detonated an entire economy. Uber. Instagram. A $400 billion industry that, 12 months earlier, simply did not exist. No one voted for it. No one engineered it on purpose. Faster wireless made the impossible suddenly ordinary, and money poured toward whoever got there first. So when 5G arrived, the promises were staggering. A surgeon, guiding a robotic scalpel through a patient an ocean away. Fleets of driverless cars negotiating intersections without hesitation. Factories moving as a single synchronized organism. None of it happened. Not on schedule. Not close. So what went wrong? Physics did. Old, stubborn, indifferent physics, a rule so elementary a child could learn it in under a minute, and yet no engineer on Earth has ever broken it. A wireless signal is simply a wave. Some waves move slowly. Others move violently fast. And that single difference is the whole story. Slow waves are built like armor. Rain doesn't stop them. Walls barely slow them. They can travel for miles without losing their nerve, which is precisely how a listener decades ago could pull in a crackling baseball broadcast from 3 states away on nothing but AM radio. But armor is heavy. A slow wave can carry almost no information. Picture a voice shouted across an entire stadium. The sound arrives, but only a handful of words survive the distance. Fast waves are the inverse, reckless, brilliant, and short-lived. Because they oscillate so violently, each pulse can smuggle in a fragment of data, letting them carry staggering amounts of information in an instant. But they shatter easily. A single wall halts them. Rain scatters them into nothing. They collapse within a few hundred feet. Think of it as a secret whisper directly into someone's ear, extraordinary detail, but only if you are close enough to feel their breath. Speed or distance? Never both. That has been the unbroken law of wireless communication since the very first signal left an antenna, and it is exactly why 5G quietly failed you without you ever realizing it. The dazzling version of 5G in the commercials runs on the fastest, most fragile waves in existence. Magnificent in a laboratory. Nearly useless in your pocket. A tree can kill it. A window can gut it. Your own hand, wrapped around your phone, can quietly sabotage the connection. So, what are you actually using day to day? A modestly improved version of 4G, 200 to 500 megabits per second. Better than a decade ago. Nowhere near what was promised to you. Say that back to yourself slowly. The screen reads 5G. The experience never truly changed. And this was never merely about buffering. Remote surgery. Autonomous convoys. Fully robotic factories, none of it is possible without speeds in the tens of gigabits per second and delays too brief for a stopwatch to register. Ordinary 5G isn't in the same universe as that requirement. Now consider the scale of what China poured into solving this anyway. By the end of 2025, the country had constructed 4.5 million 5G towers, more than every other nation on the planet's combined. Over 1 billion people connected. And still, the speeds people actually experienced were a fraction of what the technology had promised. The infrastructure was finished. The physics simply refused to yield. That is the exact moment a group of Chinese researchers stopped asking how to improve 5G and asked something far more dangerous instead. What if you stopped negotiating with the limit altogether? What if you reached past it, straight for the fastest wave that exists anywhere in nature, a wave so extreme that in the entire history of human communication, no one had ever tamed it into something usable? That wave has a name: terahertz. Remember it. Because the chip, the breakthrough, and the reason intelligence agencies across the world are suddenly watching Nanjing so closely, every part of it traces back to those 4 syllables. Here is why terahertz waves were written off as a lost cause. And once this sinks in, everything that follows will hit differently. Terahertz waves can carry a staggering volume of data, more than anything 5G touches today. But they're almost unbearably fragile. The faintest trace of moisture in the air is enough to wipe them out. A single wall stops them cold. Even ordinary humidity on a warm afternoon is enough to weaken the signal into nothing. For decades, scientists had a name for this stretch of the spectrum: the terahertz gap. Enormous potential, sealed behind a door nobody could pry open. It was the equivalent of engineering an aircraft capable of hypersonic speed, only to watch it crumble the moment it tried to taxi down a runway. Teams in the United States, in Japan, across Europe, all took their swing at it. All walked away with nothing. This wasn't a shortfall of ambition or investment. It was a wall built by physics itself, and physics does not negotiate. And it got worse before it got better. Every wireless system ever built processes signals through electronic circuitry, and each frequency demands its own dedicated hardware pathway: a separate amplifier, a separate filter, a separate antenna, wired in like a department that only speaks one language. A 5G tower, underneath its casing, is really a stack of these single-purpose departments bolted together, one for every frequency range it needs to handle. Functional, yes, but bloated, costly, and mechanically clumsy. Now here is the piece of this discovery that leaves engineers either thrilled or deeply unsettled, depending which government they answer to. A team at Peking University, working alongside City University of Hong Kong, threw out every one of those single-purpose departments and replaced the entire stack with a single chip. The trick is almost absurdly elegant. Rather than processing a signal the conventional electronic way, the method every wireless system before it had relied on, their chip converts the signal into light, handles it entirely in that form, then flips it back. Why does that change everything? Because light is indifferent to what it's carrying. A single beam can move a low-frequency signal, a high-frequency signal, or a terahertz signal with no distinction between them at all. Instead of 10 separate departments each fluent in only one language, everything gets translated into the one universal language of light and routed through a single channel. That chip runs 11 millimeters long and under 2 millimeters wide. You could lose it inside a shirt pocket without noticing. And on that sliver of silicon, it handles 9 separate frequency bands at once. 9 hardware modules that currently fill an entire 5G tower, condensed onto a piece of silicon barely large enough to see clearly with the naked eye. What does that actually mean for you? If a single chip can replace an entire equipment rack, a wireless tower stops being expensive, bulky infrastructure and becomes something closer to a household appliance. A rooftop antenna that once demanded a closet full of gear could now run out of something the size of a shoebox. Multiply that across millions of towers worldwide, and this stops looking like a laboratory milestone. It starts looking like an economic one. But there's a second layer here, easy to miss on first pass. If one chip can handle every frequency band simultaneously, including terahertz, the old trade-off between distance and velocity simply dissolves. The same hardware can lean on slow waves for coverage and switch to blistering terahertz waves for raw speed on demand. When the team published their results in the journal Nature in September 2025, the chip had reached 100 gigabits per second on a single channel, enough to pull down 2 full 4K films in 1 second flat. It switched between frequency bands in under 200 microseconds, a gap of time too brief for the human eye to register as anything at all. Even that wasn't the full picture. A completely separate team, working out of Purple Mountain Laboratories in Nanjing alongside China Mobile and Fudan University, took the exact frequencies the rest of the world had abandoned and pushed a signal through open air at 206.25 gigabits per second. Not a projection. Not a lab estimate. An independently verified, publicly reported measurement, roughly 20 times faster than the 5G connection in your pocket right now. Now hold both discoveries in your mind at once. One team compressed an entire tower's worth of hardware into something the size of a fingernail. Another proved the fastest wireless frequency in existence actually functions in the real world. Both teams the same country. A country that already has more wireless infrastructure buried in its ground than any other nation on the planet. And the timeline deserves its own moment of attention. A signal at terahertz speeds was first clocked in 2022. 3 years later, the light-based chip made it into Nature. And on April 21, 2026, China announced that a live pre-6G network had switched on. This wasn't confined to a laboratory or a sealed testing facility, it was running across an actual city. Nanjing. 10 base stations, real streets, real data. Engineers on the ground reported speeds up to 10 times faster than current 5G, running applications that sound lifted from a different decade entirely. Drones broadcasting live footage without a flicker of lag. Factory machinery taking wireless instructions as instantly as if a cable were plugged straight into them, and holographic calls, a living, three-dimensional image of a person, transmitted in real time. None of that is a promise for later. It is running right now in a city you could walk through today. Behind that single city stood a number large enough to explain everything else in the story: $485 million, folded directly into China's national blueprint for 2026 through 2030. A plan that ranks 6G alongside artificial intelligence and quantum computing as a national priority, not a side project. Nanjing has since taken to describing itself as the planet's inaugural 6G city, with Huawei, Qualcomm, China Mobile, and Ericsson all standing behind it. And that is precisely the moment the rest of the world stopped watching and started sprinting. South Korea, the nation that got 5G off the ground faster than anyone, committed $2.2 billion toward its own 6G program, with real pilot services targeted for 2028. Samsung and LG each launched their own terahertz testing efforts. There's that word again, resurfacing inside yet another country's laboratory. Japan and the United States joined forces on a $4.5 billion partnership built, in no small part, on the fear of being left behind. The European Union poured over $100 million into research scattered across the continent. Tally it all up, and by early 2026, global 6G spending had crossed $20 billion. 3 nations alone accounted for close to 3/4 of that entire sum: China, South Korea, and the US. When that many nations move that much money that quickly, they are not placing a hopeful bet. They are reacting to something they have already watched happen. Nokia, once among the untouchable giants of wireless, has openly acknowledged that the world's wireless research hub is drifting toward Asia. Ericsson's own forecast, published toward the end of 2025, put commercial 6G networks arriving around 2030, with China the likeliest to get there first. The global body responsible for writing the technical rules every phone on the planet must obey has already locked in a 2028 deadline for 6G specifications. This race isn't approaching. It is already underway, and not every competitor is starting from the same starting line. Here's the piece of this puzzle that outweighs the money entirely. Inside the rooms where global wireless standards actually get negotiated, the rooms deciding which technology every phone and every tower on the planet will run on. China now controls close to 40% of every 6G patent filed anywhere on the globe, a larger share than America, Japan, South Korea, and the whole of Europe hold when you add them together. In plain terms, whoever writes the rulebook for 6G will have more influence over it than every other nation put together. And the author of the rulebook doesn't merely lead the technology, it decides who else gets permission to use it and under what conditions. This isn't theoretical. The Nanjing network has been operating continuously since April 2026, exposed to genuine weather, genuine buildings, genuine interference. China's government has confirmed it completed its first round of 6G trials between 2022 and 2024, generating more than 300 verified technologies. A second round is underway right now. A third, covering pre-commercial hardware, begins in 2027, the same disciplined, staged approach that let the country build the largest 5G network on Earth in under 5 years. Let's be honest about what stands in the way, because there's real friction here. Terahertz signals still can't pass through walls. They still struggle against humidity. Blanketing a city properly would require transmitters mounted on nearly every building, not merely every block, and the electricity bill for running that many transmitters continuously is enormous. On top of that, American, British, and Australian regulators have each already barred Huawei from their 5G infrastructure over security concerns, and that friction will only intensify as 6G grows in importance. Nations that adopt Chinese 6G technology gain access to the most advanced equipment available, but they also become tethered to Chinese supply chains. Nations that refuse it risk falling behind entirely. Sooner or later, every country on Earth will be forced to choose a lane. And there's a quieter problem rarely discussed. Building 6G demands people fluent in wireless engineering, artificial intelligence, materials science, and advanced manufacturing, all at once. China has openly admitted it doesn't have enough of these specialists. Neither does anyone else. 6G isn't one discipline, it's a dozen disciplines fused together, and the number of people on the planet capable of operating across all of them is vanishingly small. None of that erases what the science has already proven. It only determines how long the road runs between a working prototype and a network serving 1 billion people, and every prior wireless generation has faced that exact gap and found its way across. Here is the larger pattern worth sitting with. Every generation of wireless technology has quietly redrawn the map of global power. 2G handed Europe that authority, since the standard itself originated there, with Nokia and Ericsson building the infrastructure the world came to rely on. 3G shifted it toward America, since American companies built the smartphones riding on top of it. 4G cemented that dominance, because the entire app economy was born in Silicon Valley. 5G was supposed to continue that streak until China erected more wireless towers within 3 years than the rest of the developed world managed altogether, and the axis began, for the first time, to tilt. With 6G, China isn't merely chasing the fastest network. It's reaching for the patents, the chips, and the standards, all three, simultaneously. Should that effort land, everything from how your phone actually operates, to which equipment your country's network is built on, to who collects payment each time the technology gets used, gets decided in Beijing. In 2027, the World Radio Communication Conference will divide up the spectrum above 100 GHz, the exact territory where terahertz waves live. The nations that arrive at that table with working results will help shape those rules. The nations that arrive with slideshows will simply watch it happen. China currently holds roughly 40% of the world's 6G patents. It has 4.5 million 5G towers already anchored in the ground. It has a functioning pre-6G network running through a real city. And it has close to $500 million committed specifically to making 6G commercially real. No other nation on the planet holds all 4 of those pieces at once. The era built on 4G never announced its own expiration date. It simply began losing ground to something faster, engineered by people willing to spend the money and absorb the risk, while everyone else was still debating whether to begin. That shift is unfolding right now, only this time, the gravitational pull isn't coming from Silicon Valley. It's coming from Nanjing, tucked inside a sliver of silicon no bigger than a fingertip, fluent in every wireless language ever devised. History does not wait for a vote. It rewards whoever finishes the sentence first, and by the time everyone else agrees on what to call this technology, China will already be collecting the toll on it. The next great wireless age will not be announced. It will simply arrive, already built, already patented, already running through a city most of the world had never thought twice about, and the rest of the planet will spend the next decade discovering, one contract and one license fee at a time, exactly who is left holding the bill.